Hey Chem Kids, Campbell here. In this video, we're going to go through first a review of all the different types of intermolecular forces, some of their properties, and then we're going to look at how do we figure out if something is a solid, liquid, or gas at room temperature, or if it has high melting or boiling points or vapor pressure. So the first thing I want you to do is, if you have the notes packet, you've already got this table in it. But if you don't, if you're just doing this in your notes, then what I want you to do is I want you to make a table with the columns that say type of bond. Those are the intramolecular forces, or the forces between atoms inside a molecule. Type of intermolecular force, or IMF, that's inter means between molecules. A column that says when, so we can identify when we have these. The properties, and the state at room temperature. And also we can put down some examples. The first one I want to talk about is ionic. So remember in our last unit we talked about ionic bonds. Those are the intramolecular force, but they're also called ionic when we're talking about the between molecule forces. They're also called ion-ion forces, but we're going to call them ionic. Remember last unit, we learned that an ionic compound was when we had a metal bound to a nonmetal, or the electronegativity was greater than 1.7. But that's kind of, the 1.7 is a little fuzzy. So the easiest way to identify them is if that first atom in the formula is a metal, and the second one, it's bound to something else, the second one's a nonmetal, you have an ionic compound. So make sure on your periodic table you have written down where the metals are. Makes life so much easier, because then all you got to do is look at the first element and be like, oh, it's a metal. It's bound as a nonmetal, ionic. Some properties, you learned about these in the first video, but it's good to keep them in one location, so let's write them down. Ionic compounds have high melting and boiling points. They are brittle, they are hard, and they do not conduct electricity unless they're liquid. So what does this stuff mean? Well, brittle means that if you had like a plate of it and you went to try to like bend it, it would just break. It wouldn't bend at all. So brittle is something that just breaks, like a dry stick. You try to bend it, it just breaks. They're very hard. Like if you take sodium chloride, right, table salt, and you put it on your hand and you try to rub it together, it kind of hurts. And they don't conduct electricity. Like if I take a block of sodium chloride and I try to run electricity through it, doesn't work. But if I dissolve it in water and I make it a liquid solution of sodium chloride, an aqueous solution of sodium chloride, I can conduct electricity. Now, ionic compounds are always solids at room temperature. The next type of bond that I want to talk about are covalent bonds. Remember, we talked about those in our last unit when we talked about polar and nonpolar covalent bonds. They're also called molecular substances. In fact, we tend to call them molecules when we're talking about covalent type substances. Remember, we talked about these in the last class. The type of intermolecular forces for covalent are diverse. It depends upon what I have. So we have hydrogen bonding, we have dipole-dipole, or we have dispersion forces. And usually molecules have a combination of those. Now, how do you know if you have a covalent substance? Well, that's when we have two nonmetals bound together. And so when that happens, also the electronegativity difference is going to be less than 1.7, although there are a couple covalent substances that are a little higher than 1.7, but that's a good general rule. Now, if you go back to last class, we talked about hydrogen bonding. Remember, hydrogen bonding occurs if there's a hydrogen, but also if there's a nitrogen, oxygen, or fluorine. So it's not just hydrogen with anything. It has to be a hydrogen with an oxygen, a hydrogen with a nitrogen, or a hydrogen with a fluorine to have a hydrogen bonding. Dipole-dipole occurred in our polar molecules. So that was when we had an electronegativity difference between 0.5 and 1.7. And dispersion forces occur in nonpolar molecules. So those are the ones that have electronegativities that are less than 0.5. From a property standpoint, covalent molecules have relatively low melting and boiling points, so much lower than ionic substances. They're also soft and they never conduct electricity. Now, when I say soft, what do I mean by that? Because an example I have in the picture there is wax. Wax, candle wax, is a very large covalent molecule. And some waxes are pretty hard, but compared to something like an ionic compound, if you put pieces of wax in your hand and you kind of rub them together, it's a little softer than the rough edges of an ionic compound or a salt. Now, the state at room temperature here varies because it depends upon the size, it depends upon the type of force. So if they're solids, if they're big, like if they're very big molecules, wax, for example, is a very large carbon-hydrogen molecule. They're liquids or gases depending upon their intermolecular force and their size. So that's something we're going to talk about in a little bit. Metallic substances, we say that the bond is metallic, the type of intermolecular force is metallic, because what metallic substance is it's a pure metal. So like if I have gold or silver or mercury, those are pure metals, and so we say that they have metallic bonds and metallic intermolecular forces. So how do you identify them? If you just see a metal by itself, even if it's just sodium, Na, that is a metallic substance. They have variable melting and boiling points because it really depends on what metal it is, and they have variable hardness. So they kind of have a range in between ionic and covalent. We say they're malleable, and what that means is I can bend them. So if I have a metal sheet, I can just take that metal sheet and I can bend it. So I can't do that with an ionic substance, but I can do that with a metal, right? We can shape metals into different shapes. They're also conductors. So anytime we're running electricity, we're running them through metals. In your house, you have copper wires. Copper, Cu, right? That's a metallic substance, and it's a great conductor. All metals, with the exception of mercury, are solids. Mercury is special, and it's a liquid, but every other metal is a solid. Our last substance is covalent network. And again, the name of the bond and the intermolecular force is the same. Good examples of them are diamond and quartz. Diamond is a pure carbon compound that have covalent network bonds, very strong bonds. Quartz is another example. Quartz, the formula for quartz is silicon dioxide right here. Quartz is also very, very hard. Covalent network substances have very, very high melting and boiling points. They're hard and they're non-conducting, and they are always solids at room temperature. All right, let's talk about the physical properties some more. So one of the things you're going to have to be able to do is say if something's a solid, liquid, or gas at room temperature. And the strength of the intermolecular force really is what determines these properties. So what I want you to do on your pages, I want you to write down from strongest to weakest the intermolecular forces. So our strongest force is an ionic force. That's the strongest. Because we're leaving out covalent network. Really, all you need to know about covalent network are some good examples, like diamond and quartz. Our next strength is metallic. Metallic substances come after ionic. And then we get our covalent substances, right? These are our covalent intermolecular forces. Covalent is the bond name, or the intramolecular force name. The intermolecular forces depend. So we have hydrogen bonding, which is stronger than dipole-dipole, and dispersion forces are our weakest intermolecular forces. And strength determines, is it a solid, liquid, or gas? The stronger the intermolecular force, the more likely it is to be a solid. So what we're going to do is we're going to kind of make some breaks here. So we're going to say anything ionic, so metal bound to a nonmetal, and anything metallic, except for mercury, is going to be a solid at room temperature. Now, covalent substances, remember I said they could be solid, liquid, or gas depending upon like their size and their forces. And how are you going to know? Like, how are you going to know that something that with dispersion forces, if it's a certain size, could actually be a solid? So what we're going to do is we're just going to make some cuts here, just for the purposes of you having to answer these kind of questions. So what we're going to say is that anything with hydrogen bonding is going to be a liquid, because most of the time that's true. Water has hydrogen bonds, even though it's small, it's a liquid. A lot of the alcohols have hydrogen bonds. They are liquids. We're going to say anything that's dipole-dipole or dispersion force, those are going to be gases. So, and really, like I said, it depends, because there are stuff with hydrogen bonding that are gases, like ammonia, but, you know, we're just going to make these cuts and we're just going to go with it. So make sure you write down Ionic and metallic are solids. Hydrogen bonding, we're going to say, are liquids. And dipole-dipole dispersion forces are going to be gases. All right, the next thing I want you to do is I want you to make this little line here, and we're going to cut it right here. We're going to say that ionic and metallic have high melting and boiling points, right, and low vapor pressures, vapor pressure being the exact opposite of melting and boiling point, and that anything with hydrogen bonding, dipole-dipole, or dispersion forces are going to have low melting or boiling points. But if we had to rank them, if you had to rank like highest to lowest, you're going to rank in this order. So the highest melting points will be anything with ionic, and then metallic, then hydrogen bonding, then dipole-dipole, then dispersion. Anything with a low vapor pressure, right? Vapor pressure, remember, is the pressure of the vapor over the liquid. Anything with low vapor pressure is going to be a solid. So if we had to rank stuff, we'd say that ionic has the lowest and that dispersion forces have the highest. So when we do rankings, we're going to rank things in the order that is shown on this little chart. So let's talk a little bit more about vapor pressure. So I talked about vapor pressure in the first video. Vapor pressure is the pressure of a gas above a liquid in a closed container. Every substance evaporates. And so if we, even if a solid, right, if we put it into a container, some of it's going to evaporate. And remember that pressure comes from collisions of molecules with the walls of their container and other substances. And so the more gas you have, the more vapor you have, the more pressure, vapor pressure you have. So it is the opposite of melting and boiling point, because the more you're a vapor, the more vapor pressure you have. So things that have strong intermolecular forces, like our ionic and metallic, are going to have very low vapor pressures. But things that have weak intermolecular forces, that are liquids and gases, have very high vapor pressures. Now, another thing that comes into play with our covalent substances, right, is that they could be solids, liquids, or gases. And we're going to make the cut at hydrogen bonding is a liquid, and dipole-dipole and dispersion are gases. But the size of the molecule also plays a really important role in what it is. And the larger molecule, the stronger it is, the more intermolecular force it has. And so remember, things that have stronger intermolecular forces have high melting and boiling points. So here is a graph of boiling points. And I want you to ignore these guys for a moment, but this is the boiling point per molar mass, molecular weight, right? Molar mass from the periodic table. So I want you to look at this navy blue line here. You can see that here, or maybe it's not really navy, but this is darker blue line here. You can see here's CH4, carbon with 4 hydrogens. It's small. It has a molar mass of about 20. And then here is silicon tetrahydride, or SiH4, that is a little bigger on the periodic table. And as we go up, you can see that the boiling point is increasing as the size from the periodic table goes up. And you'll see that trend for everything but these guys that I put a circle around. What's so special about the guys I put a circle around? Why are they're small, but why do they have such high boiling points? What's different about them? Well, if you said hydrogen bonding, you are correct. Remember, to have hydrogen bonding, you have to have hydrogen bound to an oxygen, a nitrogen, or a fluorine. It can't just have hydrogen bound to anything. And so these are special because of the hydrogen bonding. So hydrogen bonding is more important than size when it comes to something like boiling point. So force matters, size matters, but like I said, we're going to do some cuts. But if you had to pick, if you have two covalent molecules that have dispersion forces, for example, and you had to pick which one had the higher boiling point, well, you'd have to go to the periodic table and calculate its molar mass. All right, let's do this. Let's determine if something's solid, liquid, or gas and rank them for melting, boiling, and vapor pressure. So in order to do that, first thing we have to do is figure out what is the intermolecular force. So that's what we're going to do first. We're going to figure out what is the intermolecular force, and then we can fill the rest out. So this is the most important skill you can have. What is the intermolecular force? So let's look at the first one. The first one is lithium fluoride, LiF. So what I want you to do, this is the procedure I want you to follow every time. The first thing I want you to do when you look at a substance, look at the first element, if it's a compound, and go to your periodic table and determine if that is a metal. If I go to the periodic table, you'll see lithium is in that first column with the alkali metals. That makes it a metal. Fluorine is a nonmetal. So a metal bound to a nonmetal is ionic. So this is an ionic compound. All right, let's take a look at N2. N2, first thing you want to say is it a metal? No, nitrogen's not a metal. Nitrogen's bound to itself, in fact. So anything bound to itself, right, has an electronegativity difference of less than 0.5, right? That's going to be 0. So this is going to be nonpolar, and remember, nonpolar intermolecular forces are dispersion. All right, on to the next one. Ask yourself, is the first thing a metal? No, hydrogen's not a metal. I know it's over by the metals, but it is a nonmetal. All right, so once you've answered the question, no. The next thing I want you to do is, if it's a nonmetal, you got to ask yourself, is there a hydrogen? This one has a hydrogen. And is it bound to a nitrogen, oxygen, or fluorine? Well, it's bound to an oxygen. So this makes it hydrogen bonding. All right, next one, Au. Ask yourself, is Au a metal? Yeah. Do you know what metal that is? That's gold. Is it a metal bound to something else? Is it a metal bound to a nonmetal? No, it's a metal by itself. So that makes it metallic. All right, on to this next one. Ask yourself, is the first thing a metal? No, carbon's not a metal. Okay, that means it's going to be covalent because that's a nonmetal. So then we got to ask ourselves, does it have a hydrogen? And we would say, oh yeah, we got a couple hydrogens here. And then we got to ask ourselves, is the hydrogen bound to an oxygen, nitrogen, or fluorine? Oh, yes, there's an oxygen. So that makes this hydrogen bonding. I'm just going to abbreviate that. On to the next one. Is that a metal? No, nitrogen's not a metal. So that makes it covalent. Then ask yourself, is there a hydrogen? No, there's no hydrogen, so there can't be hydrogen bonding. Then go to the periodic table and look up the electronegativity difference between nitrogen and oxygen. And unfortunately, I don't have my periodic table with me. But if I did, I would see that the electronegativity difference is greater than 0.5. So anything that makes it polar, anything that's polar is going to be dipole. Okay. So now, solid, liquid, or gas. All right, we said that anything ionic was solid. We said anything that was dispersion is going to be a gas. Anything with hydrogen bonding, we said it was going to be a liquid. Anything that was metallic, unless it's mercury, is going to be a solid. Hydrogen bonding, again, we said it was going to be a liquid. Dipole, we said it was going to be a gas. See, once we have the force, it makes it so much easier to figure out what the solid, liquid, or gas is, the state of matter at room temperature is. All right, next we're going to rank boiling points. Okay, so if we go back to the table, remember it went ionic, metallic, hydrogen bonding, dipole, dispersion. So we got to go find ionic. Ionic's going to be number 1. It's going to be the highest. And our dispersion is going to be the lowest. So if I go 1, 2, 3, 4, 5, there's 6 of these. So this is going to be the lowest. Dispersion forces are the weakest. After ionic comes metallic. So that's going to be number 2. After metallic comes hydrogen bonding. Well, we have 2 for hydrogen bonding, right? We have H2O and C6H13OH. So then we have to look at size. Who's bigger? Bigger is stronger. So that's going to be next. Well, obviously C6H13OH is bigger. So that's going to be 3, and that's going to make water 4. And after hydrogen bonding comes dipole. So that's number 5. All right, last thing we're going to do is rank vapor pressure. Well, now that we have our boiling point, we just flip it. So whatever's 1 becomes 6. Whatever's 6 becomes 1. So we just go through that. So 5 becomes 2, 4 becomes 3, 3 becomes 4, and 2 becomes 5. So you just flip them. Once you know 1, just flip to get the vapor pressure because it's the exact opposite. All right, long video, I know. Time to move on and do some work.